All right, good afternoon, everyone. My name is Issa Nesnas. I'm a JPL technologist. I'm also the associate director at CAST. And I also have a role that I sit on NASA's capability leadership team. So I will cover today autonomy for space applications. This session, I will kick this off. We have several speakers in this session, and I'm going to, within the context of my talk, tell you how these work together and plug together. But I do want to take a step back, and I want us to look at what is autonomy, when do we need it, and why. That's an important question that comes up in the work that we do. And it is important to think about it because it has different meanings depending on the context you use. So let me start off by the definition. According to NASA's definition of autonomy, it is the ability of a system to achieve goals while operating independently of external control. That definition was based on an earlier definition, but was put out in the public domain in 2018. So in this definition, there is a system. That system is autonomous from some kind of external control. Now, so that system is interacting with some external entity, and an example is a robotic spacecraft. All of JPL's business is building some kind of a robotic spacecraft, and that's independent from the ground system that's commanding and controlling this autonomous system. But in the NASA context, that's not always the case. The system actually, in the official definition, could be humans and machines. So think of a crew on a spacecraft on their way to Mars. Those could be autonomous from the ground. So this means that the humans and machines have to work together to come up to decisions, to be independent. The external entity is not always the ground. It could be an orbiting craft, it could be Gateway around the moon, and the crew on the surface of the moon is autonomous from Gateway. So the bottom line is autonomy is relative. So when we talk about autonomy in the context of space applications, what is autonomous from what? Now, another question that comes up often is, when do we need autonomy? And that's really important because with every mission concept, we always ask that question, when do we need it, under what conditions? There's two parts to this. The first part composed of three things. When there are changes in the environment of the spacecraft, and when we cannot predict these changes, and when we need to respond before the next communication cycle. When all three are true, we do need autonomy. But there's another part to this, which depends on how we set our goals. If we set a very, very ambitious goals, even though this could be achieved without autonomy, where you put the goalpost determines whether you need autonomy or not, which plays into the one on the left here. So what I mean, say if I ask the system, we need to design a system that's going to go and collect X number of samples within this mission duration. How you set the mission duration determines whether you need autonomy or not, depending on the cadence of communication, the ground operations, and so forth. So the need is really driven by the spacecraft, the environment, and the goals that you set. Now, let's look at why do we need autonomy. And so I'm going to go back in history and look at past, present, and future. In the past, we've flown a large number of spacecraft. There's been a lot of flybys, and then we've seen a large number of orbiting spacecrafts. There's also been, at the present time, a larger number of in-situ spacecrafts getting on the surfaces of planetary bodies and doing more things on the planetary surfaces of bodies. And in the future, we are seeing even different types of spacecraft with more ambitious goals. So if we look at the trajectory from the past to the future, I'd make the argument that the number of unknowns, when we get onto planetary bodies, into planetary bodies, or in the atmospheres, we're dealing with a larger set of unknowns. The models, especially when we're looking at a lot of the past spaceflight, has relied on understanding orbital dynamics, which we could model quite well. But also we've seen by operating for 2 decades on the surface of Mars, that the interactions of these entities with the planetary bodies could be quite complex, especially when you start physically and having forceful interactions with the body. You're driving, you're drilling, you're penetrating, and the same thing will occur when we go to ocean worlds. The data volume that we're getting from our spacecraft is continuously increasing, in particular in the area of perception, where we have a richer set of perception sensors on these missions. And the other thing we're seeing is the form of explorers, and that ties into the themes of that CAS put out, the moonshots, is that we've seen rovers, we've seen balloons, we see robotic arms, we see melt probes, we see penetrators, snake concept, rappelling systems, and so forth. And the form of robotic explorers is going to continue to diversify. So the argument in the past, been very successful in spaceflight, is because we have been able to predict in advance, well in advance, weeks in advance, how the spacecraft will behave. But in the future, as we get into more complex situations with larger uncertainty, we're going to need a greater flexibility. And that's how this ties into autonomy, to allow us to have greater flexibility. And that's not easy, but it's something that we're going to have to deal with, especially when we start interacting with these planetary bodies. Now, a look at missions today. So if this blue line is the mission duration, JPL has been doing autonomous capabilities from the early days. And there's been, but also, even though there has been some autonomous capabilities have been demonstrated, there's quite a bit of interaction of the spacecraft with the ground, and the spacecraft are still sequenced with large operations team. Now, there are situations where we actually are deploying autonomous capabilities fully. Consider entry, descent, and landing on Mars. We do that without ground engagement because it's not possible. We have to react before the next communication cycle. But what happens before we deploy an autonomous capability, there's a ground team to do an assessment. We deploy the capability, and then we do ground analysis afterwards. Now, what we work on today is expanding these and being able to operate autonomously for larger periods of time. Now, consider a future where the spacecraft actually is operating largely autonomously with interaction with the ground in a more supervisory mode and more intense interaction during the science engagement phase. And so that's a continuum between today and tomorrow, but there's quite a bit of opportunity to advance capabilities towards space missions between where we are and where we could go. And ultimately, what we want to do is be able to go from having very large operations teams to smaller teams that can interact with more autonomous spacecraft. So one of the key aspects to doing that is to be able to understand how do we architect autonomous systems. So part of the autonomous system is what goes on board. And to be able to advance this thing, we need a high fidelity simulation that simulates the different aspects of the spacecraft, and we be able to understand the ground engagement of the autonomous spacecraft with the ground system. Of course, everything has to be done with a science engagement to understand what kind of science objective we're trying to achieve. But equally important to building the autonomous system, both the onboard and the ground, is to understand what test infrastructure do we need and how do we VNV it. And later on in this session, you're going to hear Mitch Ingham talk about the testing and VNV infrastructure for autonomous systems that were developed under a project called DARE, which stands for Deep Space Autonomous Robotic Explorer. And Scott Livingston will talk more about taking some of these techniques and applying them to planetary roving missions. Now, if we zoom in on what is on board the spacecraft, in the most simpler form, there's two parts to the system. First part is the reasoning system. And that system is interacting with another part of the system, which we call the system that's reasoned about. The system reasoned about is made of multiple subsystems with different states that are interacting, and the reasoning system is interacting with the system reasoned about. Now, key to this is understanding the interaction of the different subsystems and modeling them. And you heard earlier in early talks from Anima and also with Issa is some of the work ongoing in neurosymbolic computing. Largely, we fly our spacecraft by understanding the physics of the problem. But we are also dealing with increased uncertainty. One of the challenging things for space applications is we have a dearth of data, especially when we go places we've never been before. And even when we think we understand the environment, there's always surprises. And you just look at the different planetary mission, and you see there's been a number of surprises. So one of the things, how can we combine the physics, which we heavily rely on, because that's the thing we always can rely on, with some more data-driven techniques to build up systems that are much more reliable, that don't need a significant amount of training data, and that can adapt in the environment they're operating in. So the big challenge is understanding all the interactions of the subsystems and those of the subsystems with the system reasoned about. So that's a deeper look into what that architecture may look like. And at the top of the reasoning system is what we call the execution, the executive. This is very similar to executives at companies. It's the orchestrator, the conductor that conducts the things that are going on within the system. We do that today with all the functions we do here is done largely with the ground operations team and a lot of expertise built over decades. But to build autonomous systems, we have not only to be able to orchestrate what goes on within the system, we have to be able to plan and handle our data, and more importantly, handle the health of the system. And all this has to work with the various subsystems that we have to care about, not just the mobility and the motion, and we heard a lot about that today, but also the communication system and the constraints that we have, the navigation and attitude control, thermal systems early on. You saw from the presentation by Aaron how system overheats. We have to deal with that extensively in space. And of course, the power system. In space, the resources are extremely limited, and it could be very challenging. So you're going to hear later on Martin Feather and Jimmy Ragan talk about health management for two different parts of the system. So an autonomous system has two parts to it. It has to actually control the system, which relies on estimating and controlling, which looks at data in the past and the now. But also an equally important loop in autonomous system is being able to predict and plan. And the work of these two together is really what autonomous systems are about. But at times, the combination of estimation and prediction is happening in a single process. For example, we do that in deep space navigation. That's a more detailed chart about how these different subsystems interact, what functions they do in the context of space missions. And in the interest of time, I do want to highlight a few things. Ultimately, an autonomous system has to do two things. It has to build awareness of the world around it and the spacecraft. And it comes in with some information about the world around it and the spacecraft from the design and what we know about the motion of planetary bodies. But often what it has to do, it has to understand what's going on with the different subsystems, reconcile conflicting information, and build a coherent picture of the spacecraft at the top level so it can take actions that are safe and effective to accomplish the mission. So later on, so Saptarshi unfortunately is out sick today, but Pio Ong generously stepped in to cover the talk, which will focus on looking at the dynamics and coordination of multiple spacecrafts for operating around a small body. I do want to touch upon, so this, as I mentioned, JPL had a long history in advancing autonomous capabilities, with early on, decades ago, in doing deep space navigation, more recently, as you've seen, with entry, descent, and landing on Mars, with surface mobility and above surface mobility. Later on, you're going to hear Marcel Veismann talk about an autonomous capability that combines landing and flying during landing, and the work that went on with CAST through that process. Now, one of the things that we've been looking at is what drives the next the next decade of exploration is what comes out of the Planetary Decadal Survey. So we did an analysis, and we learned that there's an increasing demand and need for autonomous systems. I won't dwell on that. There's a mission called the Endurance rover, which is a lunar rover that's going to traverse 2,000 kilometers on the moon, and that's a concept that's being studied at the moment, and that actually will drive autonomy to the next level. So in summary, I'm going to argue that the need for autonomy for space applications is increasing, and that's going to challenge us in terms of how do we build these autonomous systems and assure them, and how can we do that to make these more effective, bring down the cost, and enable new missions not possible today. And with that, I want to move on to the next speaker. Thank you for your attention. Okay. Next speaker is Jimmy Ragan, and he will be talking about data-driven fault detection for spacecraft.
Hi, everyone. Thank you, Issa, for setting the stage. I think I'm going to talk about failure, which I think is an area that really captures that definition A that Issa was talking about, where you have things that change, you can't predict it, and you need to react quickly. So I'm a graduate student working with Professor Soonjo Chun in the Autonomous Robotics and Controls Lab. And the algorithm I'm going to talk about is safe fault estimation via active sensing tree search. But before I get there, I'm going to start with a motivating example that might unfortunately be familiar to a lot of us. Driving on the road and someone's about to cut us off. I was taught to drive defensively, and ideally, not always, but ideally the way I try to approach these is to reason about the future scenarios and how my interactions or other drivers' interactions could affect my safety, others on the road, and try to reason about the best way to approach these. Now, the first instinct is tempting, is just say, well, I was here first, I have the right of way. Why should I yield? Why should I hit the brakes? Because it's not optimal to my cost function of getting there as fast as possible to slow down and let them come in front of me. But that might be putting myself at unnecessary risk, because what if they're not just being aggressive? What if something's wrong? What if they're nodding off or even their brakes are failed? That could lead to a collision, and that could be pretty bad. So it's better from a safety perspective to think about these types of possibilities, go, okay, it's not acceptable to run the risk of crashing just to save a few seconds. I'm going to tap the brakes, slow down, make some space. And live to see another day and not worry too much about those seconds lost. So this kind of sets the stage for the type of interactions and questions I'm thinking about. But I'm going to apply these to spacecraft instead of cars on the road. But I still want to think about the same thing. If we have spacecraft working in close proximity, how can we consider the risks that other agents might be posing to us, as well as the actions we can be taking to ensure safety while still maintaining progress on our objectives, understanding what our own health state is, things like that. And also, to tie into the data-driven aspect I'll get to at the end of this talk, as humans driving on the road, we use our experience to kind of learn to better predict these future interactions. So I know that this sort of behavior means that other driver is being aggressive and I should start to be ready to give them some space. Can agents do something like this too, to learn to better respond to these sorts of situations? So this leads me into my algorithm I'm calling SFeast, which is a method to actively identify faults. We're in particular interested about complicated fault scenarios where we have simultaneous sensor and actuation failures that can be difficult to diagnose because we have untrusted components. Is it the sensor that's broken or the actuator? They could look the same. We're also thinking about having noisy measurements and noisy dynamics. So the way we're thinking about trying to resolve this sort of situation is to take active diagnosing actions that can gather information and update our understanding of what our own failure state is. So that's what this diagram on the right here is we're going to take actions and we're going to compare what we get on the real system versus what we simulated and use that difference to update our understanding of our own health. And in particular, we might ask, what's the best actions we could take to get the most useful information that gives us the diagnosis of what's wrong with ourselves as fast as possible? And we think the way to do that is to plan test actions over a horizon. And we're going to use a tree search to do this. There's two reasons we use the tree search. One, because as we think about these actions, and as we think about this partially observable setting where there might be multiple faults that we could be happening, and there's noisy sensor measurement, so we could get lots of different observations for the same action, we need to think about these branching futures. So a tree is well suited to handle this in a probabilistic manner. Think about the information we're going to get from our actions, and also and then the update that we can make to our own belief as we take in this action observation pair. So that's useful, and it's also useful because trees tend to be fast. Monte Carlo tree search you may have heard about being used in, say, AlphaGo or other AI projects because it's really fast to execute compared to other ways of planning. And the way it works is it selects an action, it simulates what the possible future might be. In this case, we're simulating the observation we get and what update that would make to our belief if we had this action observation pair. And then we're going to compute the updated reward. In this case, we want beliefs that are as converged as possible to an underlying fault. So we're looking for observations that drive us to a better understanding of what's wrong with ourselves. That's what this darker green nodes are. And then we're going to continue to repeat this simulated process while building this tree. This is all in simulation until we reach planning horizon, return back up the rewards we got, update the values of these nodes, and start to try to steer this tree in directions that have given us better rewards, biased towards areas that have more confidence in the underlying fault. And that's something that Monte Carlo tree search has some good theoretical results, so I'm happy to talk more about how that works in the poster session afterwards. But what I want to show you is that we can use this to solve challenging scenarios, such as if we have a double actuation fault that removes control authority in one direction, in this case the positive y direction, which is going to be a problem because in this simulation, the spacecraft is starting on a collision course with this obstacle. And it doesn't know what's wrong with itself, so if it tried to just slow down by firing thrusters to move upwards, it won't work, and it might run out of time to avoid hitting this obstacle by the time it figures out what's wrong with itself. So a better approach is to take an evasive action first, try to maintain that safety, even though it might be less optimal if the worst failure isn't what's actually happening. And buys himself some time to move to the side and identify what's wrong with itself before it can start to rotate, and then gain the control authority it needs to slow down and kind of stabilize itself back in a more safe location. All while identifying what's wrong with itself and doing this. Recently, we showed we can do this fast enough in real time. I don't have the video for that, but I'm happy to show anyone who's interested at the poster session afterwards. That happened just last week. So the single agent case is starting to work. This is all great. So how do we build on this? And going back to that motivating example I started with, we're interested in faults that we can approach in a data-driven manner. And this kind of goes back to that driver experience. What can we use on our learning, knowing that when someone's speeding up on our left, they're probably trying to make the exit, even if it means we have to slow down. We're also interested in network systems. When we have more than one agent, what are these vehicle interactions or agent interactions? How do they introduce new safety, and how do they introduce new dangers? So starting with that first example, a data-driven approach to failure detection, what could this look like? I think one motivating example is thinking about faults that affect machine vision. So in this case, we've got some hot pixels on this image that a surf student made for me, a simulated infrared image. And when we don't have a lot of information, such as an infrared, where it's one channel, that could be a problem for a computer vision algorithm. It might be sensitive to this. So we'd like to be able to identify and at least, if not remove them, at least tell the operator that, hey, there's some hot pixels, you might want to expect some noisier observations than normal. But in that approach I was doing before, we were modeling these failures. And in these highly dimensional cases where we have lots of pixels in each direction, lots of things that could be nominal or failed, what's the best way to model this? It seems like there's lots of things that we would want to be keeping track of, and this could be brittle to some sort of modeling error or applying to a new system. So maybe we should take a page from machine learning and try to learn just the important behavior that is going to allow us to identify that a fault has occurred. And in particular, we want to learn the input-output response of the system when failures are present. So we know, for example, with these hot pixels, that if we change the orientation of the spacecraft, the hot pixels shouldn't move. Whereas if it was glare or saturation from a bright background object, it would. So that could allow us to distinguish between these types of faults. In this case, this is something that we might actually be able to approach with a modeling-based method, but it allows us to validate the use of using machine learning for identifying these faults. And one thing that'll be useful if we are using a learned model is that we'll be able to quickly estimate the relative probability for each fault given an action observation pair. Because as many of you probably know, once you've trained these models, running them online is fast, which leads us back to this fast planning so we can consider lots of possible futures. Because the planner doesn't need access to the full system model, this will make us have this faster planning, and it'll also make it easier to implement on new systems and deploy it quickly, because all we'll need is data. That second extension I was talking about, these network systems, introduces another range of interesting possibilities. We have new risks coming from these interactions with other agents. There's risk of collision, there's risk of impedance from getting in each other's way, but there's also increased capabilities, such as shared information and teamwork. So if we have these agents that are inspecting an asteroid and one of them's failed, hurtling towards it, that could be a problem if we aren't able to look in multiple directions at once. So we could have each agent kind of worsen its performance by taking breaks from its primary objective and looking around itself. Or maybe we could work in a team and we have another agent that's warning the others of the impending danger. This is great, but we also then, as someone who's interested in faults, I'm wondering is how can this autonomy fail? Could this cause its own problems? Such as if we're relying on communications to warn us of danger, could this introduce its own faults if these communications fail? And I think that's where my active my active fault detection approach comes in, because we could be trying to proactively test these things we're going to rely on for safety before they become safety critical. And finally, another challenge in this sort of network setting is it's, again, highly dimensional. So maybe we can learn which of these many observations we could choose across a network of agents are important for identifying failures and what actions can excite these sorts of behaviors, such as how on the road we learn certain sorts of signals that could, like brake lights coming down the highway, that can tell us that other cars are slowing down and we should be prepared for some danger. So in summary, autonomous spacecraft operations will need these sorts of robust fault detection, and SFeast is working on the single agent, so we think it could be applied to these distributed and data-driven environments. And I just want to acknowledge some of the other people who have worked with me, but I think I am out of time, so I'll stop there.
Thank you, Jimmy. Next is Mitch Ingham. Mitch is the division technologist for our systems division. He's going to talk about deep space robotic exploration.
Okay, thanks everybody. My name is Mitch Ingham. I'm, as Issa said, Chief Technologist of the Systems Engineering Division at JPL. And I collaborated with him and other people in this room on a project called DARE, Deep Space Autonomous Robotic Explorer, which I'll show a cool video of, which will take out a chunk of my time, so then I'll have to sort of blitz through the rest. But without further ado, let me go ahead and show the video so you have some context. Essentially, DARE is all about architecting and building software for autonomous exploration that we can really tackle this uncertainty problem, right? The unexplored, the challenging environments, tackle it from sort of a smart, sort of risk-aware kind of way for next generation science missions. So let me play this.
Imagine an autonomous small spacecraft heading to explore a near-Earth asteroid, map it at close distance, land, and roam its surface, all on its own with only limited guidance from Earth. After launching on a commercial rocket, the spacecraft separates, stabilizes itself, and autonomously checks out its instruments, sensors, thrusters, and antenna before it embarks on the one-year journey. It cruises autonomously to its destination, navigating by using sightings of distant asteroids with its optical navigation camera. At its first sighting of its target, the spacecraft locks its gaze onto the faint-looking body from hundreds of thousands of kilometers away, refining its own location and that of the body as it approaches. With its narrow and wide field of view cameras and powerful onboard computing, DARE starts discovering this unexplored asteroid. DARE estimates the body's rotation rate and uses its dancing silhouette to construct its shape and axis of rotation. As the images of the asteroid grow and show more detail, the spacecraft identifies and tracks surface landmarks, refining its understanding of the body's motion and shape. As it gets closer, the spacecraft reaches a hover point, turns on its near-infrared spectrometer, and starts its scientific mapping of the asteroid. Tracking its progress, it shares an initial assessment of the near-Earth object's maps and composition to the scientists back on Earth. Building a high-resolution global elevation model of the body, the spacecraft identifies possible landing hazards and candidate landing sites to send to the ground for further evaluation. Based on science and engineering information, scientists make the final decision on the landing region. Once a landing site has been confirmed by the ground team, it is time to head to the surface. DARE readies itself for its surface mission and starts its descent, controlling its trajectory and attitude toward the target to minimize rebound, streaming data to the ground for later analysis. After a sequence of anticipated bounces, the spacecraft is now ready to start exploring the surface. It self-rights and images its surroundings, establishing situational awareness. X-ray spectrometer measurements determine elemental composition for ground-truthing orbital maps. The spacecraft charges its batteries and hops to its new destination, looking back to image the patch it departed to understand surface properties. The Deep Space Autonomous Robotic Explorer, DARE, demonstrates a new paradigm in planetary exploration that handles uncertainties of an unknown world across mission phases. It is a stepping stone to more remote and extreme destinations on moons in the outer solar system that might host extraterrestrial life.
So I like that closing pen into a visualization of Enceladus there. That was one of the ocean world moons of Saturn, and we're currently sort of developing concepts and technology that will one day get us there and be able to explore in that kind of really unknown domain. So small body exploration, like the one proposed in DARE, is sort of, as it says in there, a stepping stone, right? Because it's got just enough sort of meaty and interesting technological challenge. At the same time, it's not sort of something that we is completely foreign and we can't achieve it using technologies that are sort of near at hand. So that's why it was selected for this technology demonstration mission, DARE. By the way, DARE was a mission concept that was proposed under internal JPL R&D funding. We got through sort of an initial design phase, and then the work is sort of since splintered off into a few other different technology development initiatives, including some work that Issa mentioned on the Endurance rover, which is a project that I and several others are working on now. Okay, so the key technologies that we were looking at in DARE, again, it's the onboard autonomy architecture, and Issa did a great job presenting this distinction between the reasoning system and the system that we're reasoning about. So I won't spend any more time on that. The technologies used in the reasoning system, and this was an area of great interest to me, sort of the system health management and the onboard planning, scheduling, and execution capabilities. What I'm going to focus the rest of this short talk on is V&V, so verification and validation of these capabilities. And in particular, we sort of honed in on a particular area of verification and validation of automated test generation. I'll talk about that in a sec. So what makes deep space autonomy and really the verification and validation of that especially hard? Well, we talked about the complex in situ interactions in very uncertain environments, right? So we really need to be flexible and resilient, and that really challenges our V&V. We can't replicate these environments on Earth, right? So JPL loves to apply this test as you fly paradigm, right? But really that's a fantasy, right? We rarely can test as we actually will fly, and that's especially the case when we're talking about these kinds of highly uncertain destinations like ocean worlds and the like. We've got long-lived systems, and we really can't maintain them in the traditional sense of earthbound technological systems, right? We really can just update software. So you kind of need to get it right the first time, and that's one of our compounding challenges. And then finally, these are usually one-off missions, at least the missions that JPL flies, right? And so we really don't have a lot of data, very limited flight mission opportunities to gather that data. So it's really a challenge for data-driven autonomy techniques like machine learning, which is why I'm so excited about some of these neurosymbolic kinds of techniques that bring the best of the model-based world and the data-driven world and sort of fill the gaps in our models using data. Ever-tightening budgets, practices that substantially haven't evolved in decades, the reality of our business, and a very risk-averse culture, believe it or not. Even JPL is pretty risk-averse. So there's really 4 pillars to autonomy V&V. Testing and review is still considered the gold standard in our verification and validation practice. But as we move towards the more complex behavior space for autonomous systems, these highly uncertain environments, there's much larger state spaces that need to be covered in V&V. And so we can't rely on the traditional test-based V&V that we relied on previously. So in comes analysis, right? So of course, analysis is, we have some parts of the state space that can really only be explored through analysis and simulation. Test as you fly, point from the last slide. But one area that's really ripe for leveraging analysis is how can we use analysis to focus our testing on the most important parts of the state space, in other words, the edge cases. So we're also wanted to leverage automation and, of course, architecture. How can we architect autonomous systems for easier testing? These were all themes, pillars of the V&V challenge that we were taking on in the DARE project. So I'd only have a few more seconds here, but really this is all about smarter testing, more efficient testing, and more scalable testing. And that was sort of the mantra on this project for our V&V effort. So we looked at innovations in a few different areas: test generation, runtime verification, and synthesis and composition. And we decided that for this project, due to the sort of the risk-averse culture that we were dealing with, that the biggest bang for the buck for us would be to look at test generation and maybe some elements of runtime verification. And so Scott's going to be coming up next and telling us a little bit more about the work that we have started looking at test generation. I'm just going to skip ahead to the last slide and just give you a sense of summary on the overall V&V strategy on a project like this. Goes through the full life cycle. V&V is a full life cycle activity, from architecting, which produces a specification, design, which produces a detailed design, building the product, and then operating. And there's loops to be closed here from a V&V perspective all across the life cycle. And we've got a bunch of different techniques, and Scott will be talking about test generation as a particular innovation that we were focused on in the DARE effort.
Thank you, Mitch. Scott, let's see. Okay. So next, Scott Livingston, working with Richard Murray and folks at JPL, and it's all yours.
Okay, so I'll give a quick presentation. This is work that just started a few months ago, and it's a one-year grant, so probably at the program review next year, you'll get to see the significant findings of it. This is more like a pitch. But the name of the work is Trade Study of Test Synthesis Techniques for Autonomous Space Missions. My name is Scott Livingston. I'm a former PhD student here, previously conducting research in formal methods for robotics. This is in collaboration with the team at JPL, as is probably clear from the last few talks, as well as Richard Murray here at Caltech. So there have been two main activities for this work thus far. First is to conduct a survey of test synthesis methods, and the second has been to identify some current JPL missions that are potentially can be the focus of the trade study. So you've seen diagrams like the one on the right quite a few times at this point today. The first problem for conducting the survey of test synthesis methods is to break down what autonomy is, or what autonomous systems have making them up, and therefore define the different parts that might be amenable to testing. The basic approach we're using for the survey is the high level or slow timescale operations with humans, we call it, for things like accepting commands from Earth, doing over-the-air updates, and so on. A layer below that would be more traditionally what you might think of as autonomy, which would be perception algorithms, motion planning, task scheduling, and so on. And then below that, we have faster timescale components like PID controllers and map storage and access systems and so on. So one important point here before moving on is that test synthesis is a fairly broad topic area. It's not only applied to autonomous systems. We include methods that are applied in software engineering, for example, where there isn't any autonomy. And so conducting the survey has involved trying to find how these other methods can be relevant to autonomous systems. So very briefly, we have two broad categories that I'm going to quickly talk about for the survey. One is what I would call test synthesis methods that are applicable to systems where you have a precise description of it, or you have some model. So here I just say abstractions, counterexamples, sweeps, like parameter sweeps. The basic idea is you have software, which is the implementation, but for these kinds of tests that you're synthesizing, you have an abstract model like a model description language, such as Promella, used in model checking. And this area of test synthesis methods is fairly well covered in the research literature, as you might imagine, where dynamical equations are available precisely. And there are off-the-shelf tools that can be used, some of them quite mature. We're looking at PACD, for example, developed by a postdoc here in Richard Murray's group for contract algebras, probabilistic model checking tools. Some of them were mentioned in the previous talk. and as well as Tulip, it's a temporal logic planning toolbox that allows us to, for example, construct a test, which is actually an adversarial strategy and a game model of the autonomous system. And the other kinds of test synthesis methods are good for cases where you have a full system available to run, such as in a simulation or even the real hardware itself. We refer to these test synthesis methods as being in the category of scenario generation and active learning. Essentially, a scenario is what you think of as input to some autonomy system, such as a series of waypoints, a collection of science tasks, and a description of the environment. That can be terrain, obstacles, and whatever else happens to be known. And then once the scenario is handled by the autonomous system, you get some result and then can decide if it is satisfied or not. And different from the previous slide, or methods in the previous category, generally these tools for scenario generation are useful because there is a very large input search space. And so the problem of algorithms developed for these scenario generation active learning is that we want to very intelligently select the input space. So, okay. And the slide on the right is just showing you a driving simulation, which is one area where there are actually commercial tools for generating scenarios in the case of autonomous driving on road vehicles. So for the second main activity of selecting a mission or missions at JPL to be the focus of the trade study, we've identified two. The first is Mars 2020. So as you probably know, Mars 2020 is already launched and the rover is out there. And we identified that they have an ongoing challenge in the context of Mars 2020, which is that they have new feature development in the software and they want to do over-the-air updates, which require V&V. Unfortunately, because of time constraints, they have to select some subset of the set of tests that they originally used before launch. And also there's a new feature that was developed, so they need new tests. So we think that test synthesis methods can be brought to bear on that. And the other method that we're looking at, or the other mission, sorry, is the RACER project. It's an autonomous off-road vehicle. It's an ongoing collaboration with JPL and industry. And in that case, we have access to the full software stack, and so we're exploring scenario generation as test synthesis for them. So I'll be able to give more detail during the poster session afterward. Thank you.
Thank you, Scott. Next is going to be a presentation by Pio Ong covering for Saptarshi, who's out sick today, and talking about coordinating orbits around an unexplored body.
Hi, my name is Pio. Saptarshi couldn't be here. So yeah, I'm a postdoc working with Professor Ames. And today I will be talking about safe coordinated orbits for multi-spacecraft proximity operation around unknown small bodies. And that's a long title, but I'll tell what that means, right? So we saw the video earlier from Michel that we are considering the case where we send a spacecraft to an asteroid and make a measurement of the asteroid. And the video kind of only show one CubeSat, but actually we need two in order to communicate across the asteroid body and be able to take the measurements. But anyway, so what we are interested in is we want to look at, okay, what type of spacecraft should we be sending, right? Because let's say if we send a CubeSat, which is 10 kilogram, is small, it's going to be cheap to send, but the capability is not going to be as good as, let's say, a Discovery, which is 100 times bigger. But you can take a better measurement. You can do more precise control, right? And yeah, and we really need to be precise because when we send to an unknown region or especially around an unknown body, we can have many type of uncertainties, like dynamical model uncertainties, right? Gravity field going to be different because it's an asteroid. Yeah, and as I say, the choice of the spacecraft also affect how well you perform in your control, right? So, yes. So, so this is actually, we can consider it as a safety problem. Basically, what we are trying to do, right? Let me go back a bit. So, in order to take a good measurement, for example, right, we need the spacecraft to be 180 degree. Well, ideally 180 degree. You can deviate from it a bit, right? And we don't want to deviate too much, otherwise we lose performance, right? So, so our goal is to make the spacecraft as close to, well, here's if you think the black line as 180 degrees, so you don't want to deviate too much, right? So the question is, okay, if the spacecraft is not so good at adjusting the trajectory, then we will have to do them more often, right? So we will be analyzing how, okay, the spacecraft will start deviate from 180 degrees, and then only when we start applying the control, we reset the trajectory back, we reset the safety back to being very safe, right? Okay, so here's a safety problem, but now how do you address a safety problem? Well, traditionally, right, you would be running simulations, right? You do Monte Carlo simulation, get some statistical significance to say that, hey, my spacecraft will be good no matter and robust to all type of disturbance that we can consider. But one thing I really want to note here is that the blue line is what actually would be happening, but the yellow is usually something like 3 sigma. So basically, 99% of the time, you'll be fast. You'll be doing better than whatever your statistics tell you, right? So that's really highlight the key of autonomy, right? So in real, when we send a spacecraft, instead we do all this thing on the ground, but when we send spacecraft, the spacecraft can make measurement and see how we're actually doing in real, when we apply. So yeah, we can do a bunch of simulation on the ground, and we can set many parameters to run so that we can be robust, right? And we can figure out, hey, in the worst case scenario, right, how often do we have to adjust our spacecraft in order to maintain safety, right? But as we deploy, we can leverage the autonomy to provide some feedback on how we are doing, right? And to do that, we use modern control theory that comes from robotic system that we work here. And yeah, so thank you, CAS, for bringing us together, and we really can innovate new ideas. Thank you.
Thank you, Pio, and thank you for filling in for Saptarshi on this work. Next is Marcel Veismann. He's going to talk about how to take off while you're trying to land on Mars.
Hello, everyone. So as one of the last talks for today, I just want to give a brief overview of the mid-air helicopter deployment task, which is really a collaboration between Maury's group here at CAST and folks at JPL. So one concept that's currently under development for a future Mars mission at JPL and NASA is a helicopter-only mission, and that is heavily riding on the success of the current Ingenuity system. So the reasons for having a pure rotorcraft mission is that these rotorcraft missions are significantly cheaper given the reduced weight, but also the increased mobility. So one concept that's being currently developed is the Mars Science helicopter, which has a 5-kilogram payload and can cover 13 kilometers in a single flight. So in a single flight, this system can cover a distance that a rover, these traditional ground-based rovers, can cover throughout their entire lifetime. So now comes the question of how to land this vehicle at the end of the EDL sequence when the parachute phase comes to an end. And technically, this helicopter can fly itself, so technically it should be able to land itself. But there's a number of challenges associated with just dropping the helicopter from the parachute and just having it land itself. For one, is this whole system is falling very fast, so you have almost no time to spool up these rotors, and you have to perform a very aggressive maneuver to pull out of this free fall. And the other aspect is that there are these unfavorable rotorcraft aerodynamics that come with when a helicopter just falls straight down into its own downwash. So the EDL technique that we have outlined as the cheapest, the safest, and the one that maximizes the helicopter performance, because now we don't need performance or structural margins for performing these aggressive maneuvers, is the mid-air helicopter deployment. And in this case, we're using a separate delivery jetpack, which is just strapped underneath the helicopter. And this jetpack effectively slows down the free fall and brings the helicopter to an aerodynamically suitable state that it can just take off and land by itself. We don't want to support it all the way to the surface, because in this case, we would need a huge jetpack just to deliver it all the way to the surface. And don't think of it as like a completely separate system. Think of it more like a propulsive extension. So these are just 4 dumb thrusters just strapped to the helicopter, and they're just providing us with a push to get out of this free fall until they release from the jetpack, and then the helicopter can land itself. Has a much greater selection of landing sites since it's under its own power then. So what this project is trying to achieve is essentially an experimental risk reduction campaign. So we know based on previous missions that these 2 modes of operation, jetpack and rotorcraft, are fundamentally possible on Mars, but the biggest risk that we have identified is when we bring both of these modes of operation together, which means when the helicopter is taken off from the jetpack platforms. And these specific risks are the flow interaction, which means when the thrusters are firing and they're impacting potentially the helicopter performance. And then if the system experiences relative crosswinds, and there might be resulting moments and the risk of recontact. And then the last part is the vibrational and aero disturbances that come from the jet pulsing that might push the controllers or the avionics beyond their capabilities. So in our experiments, we are performing 3 separate experiments to address these risks, 2 of them being here at CAST, where we look at the flow interaction between rotors and the thrusters, and then we're also performing dynamic takeoff experiments. And in the upcoming year, we want to go to NASA Ames to a vacuum chamber to do full-scale aerodynamic tests in relevant environments. So this is the setup that we built. So we have the helicopter, 20% scale helicopter assembly in front of the wind tunnel, and it's worth mentioning that this is oriented upside down just to avoid ground effect aerodynamics for flow studies, but for the takeoff studies we oriented right side up, and this is driven by high pressure gas here. So this is how this looks in the fan array. So in our experiments, we performed these static experiments and as well as CFD simulation that we can then compare to each other. So we found that we have a pretty good agreement between the CFD simulations of the same scenario, and then we also performed a number of flow studies just to look at how the flow is going, and then we can also compare these flow results, and we find that we have a very good match for between the CFD on the right side and our experiments that we had. And so in the final sequence now, what we're doing is we're performing this dynamic flight-off test to see if our controller can handle these aero disturbances and vibrational disturbances. So we're taken off from this pulsing platform. It's kind of hard to see, but it's vibrating here. So the thrusters are running at 30 hertz. So looking at if the aero disturbances limit our performance to take off safely. And then we also want to look at what happens if we have relative crosswinds. What is the effectiveness of trimming the helicopter before taking off? So here you have 2 scenarios. One is being trimmed, one is not being trimmed, and you can see a much greater pitching when it's taken off. So with this, I'm like a little bit over, but happy to take it.
Last but not least, Martin Feather, and Martin is going to talk about fault detection for a planetary manipulation and sampling task.
Okay, so this is for space exploration, but I'm sure you can imagine there's a lot of use for fault detection and handling autonomously in a lot of other applications too. Thomas, are you here? Where's Thomas? Okay, I was hoping he'd help me if I make mistakes. Anyway, okay, so let's get going. So, so the motivation for this is NASA's search for life in the solar system outside of Earth. And there's a strategy to look for water, because water is so essential for life. And there are 3 ocean worlds, they're called, that are known to have big oceans. Saturn's moon of Titan and Enceladus. You might remember that picture of Enceladus, or artist's impression that Mitch showed. And the one shown here, Jupiter's moon, Europa. These all have big oceans under their surface. Okay, so there's a pretty well worked out mission concept for landing on Europa and scooping up samples and analyzing them for signs of life. But Europa and those other two destinations, Enceladus and Titan, have a lot of challenges. They're a long way away. They're not like Mars. They're not next door. No. Just the light time to Europa is 45 minutes one way. And worse than that, every 42 out of 84 hours, Jupiter gets in the way, so you can't communicate with it during that period. So you don't have much communication with these things. You can't operate them from Earth. Another problem is that this one here would be battery powered, so its lifetime is limited. It's going to run out of battery after 30 days or whatever. And furthermore, there's nasty radiation, so it's not going to last long even in the best of circumstances. So imagine this thing autonomously gathering samples and analyzing them. If something goes wrong and it has to call home for help, that would waste a lot of time. So the whole purpose of this project was to look at how could you detect and respond to anomalies, faults, or whatever they are. Okay, so we're demonstrating this using a test bed at JPL, the Ocean World Lander Autonomy test bed, which has a robotic arm which can do the motion of scooping up, transferring a sample, and dropping it in a chute, which would be the onboard instruments that analyze the sample. And accompanying this, the robot arm, there's also a software simulation. So you can try things out on the software, you can try things out on the robot arm. Okay, so what are these faults? What are these anomalies? Here are some examples. If your scenario is to scoop up from the ground a sample, drop it in a receptacle, then all sorts of things could happen to make that not work. Maybe things didn't turn on right when you turned them all on. Maybe one of the arms of the robot got bent during the shock of landing. Maybe one of the sensors that tells you the joint angle is biased, or maybe the joint is just frozen. Okay, so what we do about that is this flow of information. We get information from the sensors. We know what commands were given to the robot arm. We get information from the camera, shown here, where it's taken a picture, and it can see the position of the end of the arm. All that information is flowed into a model of what would happen if everything was working correctly. And when that model doesn't agree with what the sensors are telling you, that means something is wrong. And if you have enough information, if you have redundant information, you can figure out what went wrong. So in this example, we are demonstrating that you can identify that the encoder that tells you the joint angle is giving you erroneous information. And the response to that is to then automatically recalibrate the arm. So not only are we looking at autonomy to detect faults and failures, we're looking at autonomous recovery. And I'll just finish with the team. So at Caltech, the team the PI is Joel Burdick, who I think you've heard of before. Ursine Das is the person who figured out how to do autonomous recalibration. Thomas Thume has put it all together. The JPL were led by Lorraine Fesk, and Hari Nair is the owlet arm, and that was me before I got my haircut. And then finally, Okean Solutions, they're the ones who provide this expectations model that can reason from sensor data to what's wrong. Thank you.
Yeah, thank you, Martin, and thanks for all the speakers and for all of you for listening into this session. I'm going to turn it over to Aaron Ames with some closing remarks for the day.
Great, thank you. Thank you, everyone, in this session. Yeah, no, thank you, everyone, for a really fantastic day. I was, listening and just taking in everything that's been done in the last 6 years since CAST started, and it's really incredible. And seeing the JPL and all the students present has really been fantastic. So thank you all for the time and effort. Before we close, I just want to take a second to thank the people that made all this happen, specifically Palace first. She organized this from day one, so let's thank Palace. So thank you. She really made it happen and pushed us professors to get this done. Also, Karima, who's back there, and Sarah, everybody was a big part of this. So let's thank them for all their efforts. And finally, the students and postdocs, I really want to say that they're the lifeblood of CAS, they're the lifeblood of Caltech, and they're the ones that are responsible for everything you saw today, really. So let's thank all the students and postdocs. And of course, Maury, our glorious leader. So shout out to Maury. So right now we have posters set up, and the reception starts at the Athenaeum at 4:15. So it's a little tight, but what I'd ask you to do is take a tour by the posters, check them out, start a conversation, and then head to the Ath, because we're starting at 4:15, our reception. So with that, without further ado, thank you everyone. Great day.